Okay, so till now we studied till Archimedes principle and all, isn't it? Now, the point is Archimedes principle has passed, and the major concern regarding now is that till now we have studied only those kind of fluids which were at rest, isn't it? We didn't pick up any kind of topic which were discussing fluid to be in motion. So right now we are going to start that only. Fluid dynamics. Till now we studied fluid statics. Now we are going to study fluid dynamics. Means the flow of fluids. How they are going to flow. Okay. Which is mainly categorized by Bernoulli's principle. Okay. Is that clear? So that's what we are going to start today, right now. And one of the most important thing to categorize in fluid mechanics or fluid dynamics is that what are the different kinds of nature of flows are there, means what kind of water flow is there, or how the water flows from the system or something like that. Are you able to get me or not? So right now we are going to discuss regarding that only, that what can be our different types of flows in the fluid dynamics and all. Okay, so let us start with one of the most important case, and we define one quantity to categorize the fluid, the flow of fluid, and that is called as streamlines. Okay, so we want to categorize the flow of fluids, and that is by the method of, first thing is by the knowledge of streamlines. Are you able to get me or not? So what are streamlines? Let me check this camera thing. I think I'm sharing my screen now. Okay, okay. So let me just talk about a streamline. So what are these streamlines? So they are nothing but, remember, they are just the family of curves. Okay, what do you mean by family of curves? Means there are many curves. Yeah, no, means there are many kind of lines like a straight line, parabola, or hyperbola, or something like that. So, including all these lines, all these kind of geometrical figure, we call these as curves. What we call it as? So this means that streamline are nothing. They are different kind of curvical line which belongs to one of those categories which we have defined earlier. Are you able to get me or not? But which kind of curves they are? That are instantaneously tangent instantaneously, one minute, what I'm writing, instantaneously tangent to the velocity vector of the flow. Velocity vector of any point of flow. समझो जरा, मतलब मान लो कि कोई भी फ्लो चल रहा है, ठीक है ना, कोई भी फ्लो मान लो कुछ इस तरह से है, मतलब वाटर कैसे भी ऐसे जा रहा है ना, ऐसे, ठीक. So streamline are nothing but if I can join those, like let's suppose if I selected, let's suppose water was flowing over here, and then you selected 1, 2, 3, 4, 5, 6, 7, these random points, and at these random points I know that the particle has different velocities, and if I can draw for all those velocities the tangents of them, and yeah, and if I can join these tangents, if I can join these tangents basically, then the line which is created after joining this family of tangent, we call it as a streamline. So this is called as a streamline. Are you able to get me or not? Means for every point I know the velocity of flow, then draw for all those velocity its respective tangent, join them. That line which we will get out of those tangents will be called as what? Streamlines. So many people perceive this idea as that streamline is that line which the fluid particles are following. No, fluid particles are following different velocities, but their tangents. If I join all the tangents, Then they have one common line which we call it as a streamline. Are you able to get me or not? So all the fluids are not following along this line. The velocity vector of them are following towards this line. Are you able to get me? So remember that streamlines are not the path followed by fluid particles. Is that clear? Next point. First point, they are tangent of the velocity vectors. Second point, since these are showing one direction, so streamlines, the two streamlines never intersect with each other. They are not even parallel. Their separation always remains same. Okay, there is a reason for that, because at any instant because at any instant fluid particles cannot have two net velocity. Cannot have two net velocities. Are you able to get me? Is that clear? Okay. So based upon this, we define the first quantity. Like we have distinction of flows based upon these streamline natures only, and we call it as, first one is called as streamline flow or laminar flow or steady flow, something like that. Second one is called as turbulent flow. Are you able to get me or not? So in physics, there are two kinds of flows. One is called as streamline, one is called as turbulent. Are you able to get me? Now, if a fluid is following, it will have many streamlines. Okay. One another physical meaning I'll tell you of this streamline. Why it is very very important. See, if for a fluid, if we can determine a streamline, that means on this streamline, if I select any random point, let's suppose I selected this point or this point or this point, I have an already an idea that some velocity will be present, some specific velocity will be present at these points, isn't it? So whichever other particle which is approaching from back, it will take that velocity only irrespective of its own velocity. Is that clear or not? Yeah. No, no, it's going to pick up the velocity of that point which is determined or already fixed by that streamline. Okay. And that's what makes the flow to be always in a continuous pattern. Otherwise, if they start picking up their own velocities, what will happen? Flow will disturb or yeah. So let's suppose if inside a flow I have like these streamlines. So let's suppose if I select one streamline and I selected point A, on that streamline itself, point A, B, and C. So you know that the velocity of point A and velocity of point B and velocity of point C will be already fixed by the streamline, isn't it? So that means this is true that these velocities will can be equal also, cannot be equal also. Are you able to get me or not? So at any random point, at any random point, the velocities can be different, isn't it? But what actually is the meaning of a streamline? What is the meaning of that streamline is that although these velocities are present of different nature at different point, one thing is common, that velocity at point A with respect to time will be always Constant means whatever the velocity you observed right now, the same velocity will be present tomorrow at that point, day after tomorrow also, later also. That is always going to be constant. Similarly, velocity of B on any streamline at any time will be always remain constant. Is that clear or not? So this is what they say. Streamline flow is that flow in which streamline does not change with respect to time. Does not change with time. Is that clear or not? Take. And this is what is the meaning of that. Any particle which starts means, like if it starts to pass through this point, it will start following the same path which is determined already by the streamline. Are you able to get me or not? So particles always, particle passing through any point of the streamline will start following that path which is predetermined. And that is this kind of flows which happens where the particle follow a predetermined path, and the time means the streamline remains constant with respect to time, is called as a streamline flow or a laminar flow or a continuous flow, means there is no disturbance. Okay, are you able to get me or not? Write this, then I'll move ahead. No, let us just think of another case. Let's suppose if I have a liquid flowing through this pipe, and if it is a turbulent flow, what will happen is that the streamlines will never ever be same. They will be always fluctuating, right or not? See these streamlines are never ever constant, not even parallel. Is that clear? So they can be any of shape, any kind of geometrical shape. Okay, they can be of any shape. Are you able to get me? So this is nothing. What is this? What we call it as turbulent flow? Flow of liquid in which the liquid undergoes irregular. The liquid undergoes irregular fluctuation. Flow of liquid in which the liquid undergoes irregular fluctuation is called as turbulent flow. Check. Second point, streamlines are not followed by fluid particles. Is that clear? Okay. So the question arises that how you are going to define, how you are going to just talk about these liquids. So to describe or to differentiate them on a proper basis, we brought one quantity which we also call it as Reynolds number. Okay, it's not the Reynolds pen, it's the Reynolds number, which actually tells us about that why the flow is streamlined, when the flow will be streamlined and when it will be turbulent. ठीक है? अच्छा एक बात सोचो, मतलब ये स्ट्रीमलाइन और टर्बुलेंट क्यों होता है? देखो एक बात समझो, क्या होता है कि हम मानते हैं कि कोई भी लिक्विड जो है ना, it is made up of layers. Okay, just like we have layer like books. See the books. There are pages binded together. So similarly, the liquid are made up of layers binded together, isn't it? And these liquids wants to move. So one top surface wants to move, and it wants to slide on this another surface when you just apply some force from backside. Are you able to get me or not? So when it is sliding, it will feel some friction from the down surface or not? Yes, and that frictional force is called as viscous force. Yes. Now the point is that The inertia of the body is trying to make it move forward because any kind of fluid does not have a fixed shape. So what it will do? It will start spreading, isn't it? So inertia says that you should move, you should slide, but the viscous force does not make it slide, isn't it? So this is, yeah, this is the major factor for our streamline flow or turbulent flow. That when this viscous force is less, the particles actually follow the sliding pattern, means the direction of predetermined path, isn't it? But if viscous force is higher, then this pattern changes. It becomes either here and there, and all, isn't it? And that is why we categorized that for what level of viscous force the particles will be showing turbulent nature, or for what level of viscous force the particle will be flowing streamlined nature. Are you able to get me or not? So that particular understanding for what number or what for what digit we give that condition by a name called as Reynolds number. So it is nothing but it is the ratio of it is the ratio of inertial forces which are trying to make them spread forces to the viscous forces. Are you able to get me or not? Second point, it is an dimensionless number. It is a dimensionless quantity which tells us the flow can be which categorize or which tells which is used to categorize the fluid flow pattern. Is that clear? And this is why this Reynolds number is denoted as Rn. It is given by formula rho v d divided by eta. Look over there, rho v d is just like the inertial force, while eta is the viscous force. Okay, so here we tell density of liquid, v velocity of liquid, d diameter of pipe on which the liquid is following, and eta coefficient of viscosity. And this ratio only actually tells us whether the fluid is turbulent or streamlined. So to categorize that, we have some relation. The first thing is if the Reynolds number is less than 2300, then the flow is laminar or streamlined. Are you able to get me or not? Second category is if Rn is more than 2900, then the flow is turbulent, means flow बहुत ज़्यादा fast है. Okay, is that clear? But the question is, what is there if Rn lies between 2300 and 900? So this is that reason. Still, it is unpredictable, word or not. What actually happens is here the flow changes between laminar and laminar and turbulent. Yeah, with irregular time intervals. With irregular. Yeah, yeah, there are other methods to predict it. Quite a lot. Okay, is that clear? Is this clear out? And this is the best way to categorize the streamlined flow or turbulent flow. Now, let us just talk about. We have already talked about this, but I want to still discuss that in a much more greater sense. So this we call it as volume rate flow and mass rate flow. Okay. So now, as we know that, let's suppose if through any of the uh, cross-sectional area, let's suppose I just consider some cross-sectional area. Okay. Let's suppose, yeah, just like this is perfect cross-sectional area, isn't it? So let's suppose I had any kind of pipe, okay, and from that pipe some liquid was flowing. Got it? Let's suppose some liquid was flowing. So for this flow of liquid, which is now one thing you need to remember that you do not have to study the turbulent flow. We have to only study the laminar flow, right or not, or streamline. Is that clear? So let's suppose from this cross-sectional area, if some particular what is passing, that some volume of liquid is passing. Okay. Now the question arises that from this area, that how much volume of the liquid passes in time. Okay. So you look over here. This liquid is moving with some velocity, isn't it? So in a small time, let's suppose for a small time, for very small time, I want to know that how much is the uh, volume flown by our liquid, isn't it? That's the biggest question to ask, isn't it? So in that means that in that particular time, in that very small time, the liquid will cover some length, isn't it? And that length, yeah, that length will be the area of cross section of this particular flow of fluid, isn't it? Are you able to get me? Is that clear? So now look over here. Like let's suppose if in that area, like if I ask that what is this thickness area, it's just simple. It's V into dt. That's my length in a small time dt, isn't it? So length is V into dt. Therefore, volume of liquid passing through given 1 minute passing through given cross section in dt time is how much? Simple. dv will be total volume will be what? Area into length, which is v into dt, isn't it? A small v represents velocity. Are you able to get me? So this means that dv by dt means rate of change of volume per unit time is how much? It's nothing but area of cross section into velocity. Are you able to get me or not? And this is called as volume rate flow. What it is called as? Is that clear? What does it talks about? That how our liquid flows with per unit time if it is following streamlined flow, isn't it? Now you know that volume is equal to mass by density, isn't it? So we also get mass rate flow, that how much mass has transferred within time dt is equal to nothing but density will go this side, so rho into area of cross section A into velocity v, and we call this as mass rate. Is that clear? Perfectly clear. Okay. And this was the basic building principle of our Bernoulli's equation. If the area of cross section is A, are you able to get me? Is that clear? So, based upon this, there was one conclusion, and which we also call it as, or we know by the name of, uh, not this much line, big line is required, and call it as principle of continuity. Yeah, take 1 minute. I want to give a perfect statement for this. Okay. So see that what does it says? What is principle of continuity states that it states that for a non-compressible and non-viscous fluid. Okay, means we are talking about ideal fluid. Are you able to get me? For a non-compressible and non-viscous liquid, okay, fluid which flows through a particular streamline, which flows through a ठीक है, particular streamline, then at any point of I'm framing this definition as mine definition. Okay, then at any point of that streamline, volume rate flow, its volume rate flow remains constant, remains constant. Now you see what they are saying, that if I take any kind of fluid and if it is following some kind of streamline, okay. So let's suppose there were bigger, then there were smaller, just it was getting compressed over here. Okay, over here. So see here the area of cross section is A2 and velocity of the flow is V2. Here area of cross section is A1 and velocity of flow is V1. So the condition is that at this point, let's suppose this is point P and this is point Q and this is point R. Okay. So whatever point I select, then dV by dt, volume rate flow, okay, capital volume at point P must be equal to dV by dt, volume rate flow at point R, Q, and that is equal to dV by dt at point R. And that is called as equation of continuity, or simply principle of continuity. ठीक, इसका मतलब एक और निकलता है, that means a1 into velocity v1 will be equal to a2 v2 will be equal to a3 v3 and so on. Are you able to get me or not? But the question arises that why this principle is based? Simple. This is based upon mass energy, mass conservation principle. Yeah, because whatever mass comes, that must go out, isn't it? Is that clear? Understood? Okay. So this is what's called as Bernoulli's principle, or the sorry, this is called as principle of continuity, and this provides us the basic idea that how the flow flows. And I think like you have done that derivation of Bernoulli's equation now. Should we do once again or leave it? Uh-huh. Tell me. Okay. So Bernoulli's equation. So give the heading Bernoulli's equation, and let us do once again. Did you read in exam perfectly that derivation? Let us do once again. What actually it talks about? It is only going to talk about that same thing. Let's suppose I have any pipe, okay, and that is thick at one side, thin at another side, okay. And the height difference is also there from the ground to both of these ends, okay. And we are going to talk about that. This is located at height h1, and this is located at height h2. Are you able to get me? And the liquid is flowing. 1 minute. Is that clear? Okay, liquid is flowing from here to there. Now let us suppose that the liquid has some velocity. Let's suppose I consider, means I'm just considering some uh, reason. Like let's suppose I selected some area over here. Okay, a small length. So it's better to consider in terms of, let's suppose circular. Whether I'll be able to draw or not. I am very bad drawing in. I do a very bad drawing in terms of circular ways. Yeah, so just leave it, and let us consider that I have a small width of liquid which is following, and then the some width of liquid over here. Are you able to get me or not? Let us consider a big chunk. Let us, they are very small basically, but we are considering it big because we can't solve the problem if you do not consider it big. Are you able to get me or not? So I have some big chunk of liquid which is flowing. Word or not? So let's suppose this was my liquid A and B, means initially, okay, let me 1 minute, let me just have that clear idea. Let me just, so okay, think of this case. Now try to imagine this is my one region of fluid, okay, which is present from here to there, isn't it? Yes, I call this as A and B. Okay, now as there is velocity and force from the back side, this fluid will start flowing, isn't it? And then they will move ahead. कुछ तो बोलो हाँ या ना. Yes, they will move ahead, and then they will appear over here, isn't it? Yes, this I name it as A dash and B dash. That's the displacement in fluid from that side to that side. Is that clear or not? Are you able to get me? So look over here, try to understand. Basically, what has happened due to this means why it happened, because there was some velocity v1 over here and some velocity v2 over here, isn't it? So let's suppose the velocity v1 was over here and velocity v2 is over here. Okay, and due to that, these velocities, the particles are flowing. Are you able to get me? Okay, now look over here. Let me just erase this. Okay. I call it as V1 and V2 like this. Okay, here area of cross section was A1. Let's suppose at I'm talking about one end, and here area of cross section is A2. Okay, here it is. A1, and there it is A2. Now let us just try to understand one of the most important case. एक बात बताओ, जब लिक्विड आगे बढ़ रहा है तो पीछे से कोई ना कोई तो धक्का मार रहा है ना, मार रहा है जोर से, तो जब वो धक्का मारेगा तभी तो वो आगे बढ़ेगा, isn't it? कुछ तो बोलो हाँ है ना। तो क्या हो रहा है कि एक्चुअली में जिस डायरेक्शन में वेलोसिटी है उसी डायरेक्शन में पीछे से कोई धक्का मार रहा है, लेकिन जब तुम आगे वाले पार्ट को कंसिडर करोगे तो वो तो उसके आगे भी तो फ्लूइड है ना, वो क्या करेगा, इसके ऊपर पीछे से धक्का मारेगा, है कि नहीं, isn't it? So basically this is called as pressure of the fluid. From here the pressure is P1, from here the pressure is P2. Are you able to get me or not? So for the fluid moving in forward direction, P1 from back side is more than P2 from front side. And if P2 becomes higher, the fluid will never ever flow. Are you able to get me or not? Yes. So let us just talk about all these case, and what we want to do is just we want to apply work energy theorem. What we want to apply? To talk about the flow, since we know that they are moving, the pressure are making the bodies to move, they are present at even heights, they have different velocity. So the most easiest way to talk about their flow is applying work energy theorem, isn't it? And to apply work energy theorem, I need to find, we know that the total work done is always a change in kinetic energy, isn't it? Now, here if you see, there are masses which are moving, there is a pressure which is applying one force. So we have three different kinds of energy. One, pressure energy, then the due to the velocity change kinetic energy, and due to the height change potential energy, isn't it? So let us just first talk about the work done by, means we want, the first consideration is to talk about the work done by pressure force. Is that clear or not? I want to talk about work done by pressure force, isn't it? So look over there. Due to the pressure force only, this particle gets displaced from here to here, isn't it? This fluid gets displaced from A to A dash, isn't it? So look over here. We know that, let's suppose if this displacement was done in time, means this displacement I'm just considering in time dt. Okay. So this displacement will be how much? V1 into dt from here to here, isn't it? And from here to here, this length will be how much? BB dash will be how much? Into dt. Are you able to get me or not? Yes. So I'll just write that AA dash is nothing but V1 into dt, while BB dash is nothing but V2 into dt. Are you able to get me or not? So work done by pressure force, P1 will work do the positive work. So work done by, I'm considering this is point 1, this is point 2. So work done at 1 is nothing but pressure force into area. P1 into area is A1, and the displacement done is V1 dt. The work done by second one is, that's opposite of actually minus of P2 into area dt. Is that clear? So net work done by pressure force. Simple. I'm asking for pressure force. Hmm. Into dt. That's my work done by pressure force, isn't it? Second, let us just call, no need to. We'll talk about that later. Next thing is change in kinetic energy, isn't it? Change in kinetic energy. So change in kinetic energy is nothing but kinetic energy final minus kinetic energy initial, isn't it? What is kinetic energy final? That is, kinetic energy final is nothing of kinetic energy of A dash B dash whole liquid, isn't it? कुछ तो बोलो हाँ या ना? Yes. So basically, if I want to find out the full kinetic energy, then how I am going to write? Can you give me the idea? Yeah, बताओ. I, if I want to write kinetic energy equation, Mhm. Tell me. What? Acha, what is my final kinetic energy? What is my final kinetic energy? देखो, तो kinetic energy of A dash B dash minus kinetic energy of AB will give me the net kinetic energy, the change in kinetic energy, isn't it? But what is that? Simply, what is kinetic energy A dash B dash? That is kinetic energy of liquid column A dash B plus kinetic energy of BB dash BB dash, isn't it? Minus kinetic energy of AB is kinetic energy of AA dash minus kinetic energy of A dash B, isn't it? ये कैंसिल हुआ या नहीं हुआ? तो क्या बचा? Kinetic energy of BB dash minus kinetic energy of AA dash. That's my change in kinetic energy. Are you able to get me? So what is my kinetic energy of BB dash? Simple. That is how much of my mass is present in BB dash? That is half rho. Mass is how much? How much is my mass? Mass is density into volume. Volume is area of cross section. A2 V2 dt into V2 square. This is my kinetic energy of BB dash region. Are you able to get me? This is my mass and that's my velocity. Rho, density of the liquid is always same. A1 V1 dt means density into volume, length in area into length. Okay, and that is V1 square. Is that clear or not? That's my change in kinetic energy. Is that clear? And the point is, I want to write for the change in potential energy. First, we will find change in potential energy only. That is simple. Once again, you will have to write. Once again, you will end up getting same thing. Potential energy of BB dash minus potential energy of A dash. Is that clear or not? Are you able to get me? So potential energy of BB dash is mgh. Mg is rho into area. Okay, BB dash A2 into for BB dash look over it. This is my BB dash region, no? So this is why it is. I'm considering it to be A2 into V2 dt length m. This is m g into height h2. I'm considering h2 to be nearer to BB dash. Okay, next rho a1 v1 dt g into height h1. This is the potential energy of this liquid column which is over here. Are you able to get me? Is that clear? Now we know that total work done is equal to change in kinetic energy. So work done by pressure force plus work done by gravity. There are only two forces, gravity and pressure force, and that is equal to change in kinetic energy, isn't it? So work done by pressure force is P1 A1 V1. Now we know that according to equation of continuity, A1 V1 is equal to A2, and I'm writing it equal to AB. How I'm writing it? Just AB. Okay. So here A1 V1 A2 V2 are same. So that will be taken common. P1 minus P2 AB, okay, into dt plus work done by gravity is negative of change in this potential energy. So I'll just write directly minus. I can take even a rho AV common, isn't it? DT also common, G also common, and that is minus of H2 minus H1. Is that clear? Are you able to get me? Uh, can I just move ahead? Okay. Now is equal to change in kinetic energy. What is my change in kinetic energy? Once again, A1, V1, A2, V2 same. So half rho AV dt common, and that is V2 square minus V1 square. Are you able to get me or not? So this AV dt fully gets cancelled, and we end up getting a relation which is written as minus P2 minus rho GH2 minus rho GH1 is equal to half rho V2 square minus half rho V1 square, which can be written or redirected in the form of, I'll directly write P1 plus this will be plus, sorry, P1 plus rho GH1 plus half rho V1 square is equal to P2 plus rho GH2 plus half rho V2 square, and this is called as Bernoulli's principle. Is that clear? Okay, mention it right now. Done? Now, let us have a conclusive remarks on that. So, what does Bernoulli say? That if there is a pipe, okay, and then they are located at different heights. Okay, this is located. This has area A1. Velocity of the liquid is V1. Okay, I'm just writing the coordinates. This is A1, V1, height H1, isn't it? Three things are there here: A2, V2, H2. Are you able to get me? The first conclusion is, if it is proper one streamline flow, then A1, V1 must be equal to A2, V2, which is going to be always constant for streamline flow. Second thing is, let's suppose here the pressure is P1, here the pressure is P2, isn't it? So second equation is that the pressure plus half rho V1 square plus rho क्या था इक्वेशन, रो जी एच वन था ना, हाँ, रो जी एच वन must be equal to P2 plus half rho g H2. And this we call it as Bernoulli's equation. Means that for any streamline flow, two things always remains constant. First thing is area into velocity always remains constant. And second thing, this is what? Mass relation, mass conservation, isn't it? And this equation, pressure plus half rho V1 is V square plus rho GH is also going to be always constant. That means what? This is my energy per unit volume, isn't it? Energy per unit volume conservation. Are you able to get me or not? Is that clear? And that is why we define this quantity as kinetic energy per unit volume, and this as potential energy per unit volume, because rho is nothing but mass by volume, isn't it? Yes. So one is following energy equation, one is following mass conservation, and that's why these two makes the one of the most conclusive remarks of the whole fluid mechanics. Is that Is that clear or not? Are you able to get me? Is that clear? So, 1 minute, let me check if there are anything else. Okay, so what I'm planning is today we are going to 1 minute, let me just stop this recording. So, let's stop.